Okay, I'm going to close the poll now. Okay, let me share the results. So I hope you guys are able to see the results. So what is a quantum channel? It is not a physical medium, or it can be a physical medium, but that's not what it is. It is any operation or process that changes one density matrix into another. So people who have answered that it is only a physical medium, that is not really true, that it could be any operation or process that can change one density matrix into another. That's the most general. So a physical medium would be a subset of this process, right? The trace preserving condition of a quantum channel ensures that the output is also a density matrix, right? So 4 of you answered something else. So if you are randomly picking that, please make sure you're following what it is. If you're not following, you should ask questions. I would have really loved to see everybody answer it correctly. And in the Krauss representation, um, yes, most of you answered it correctly, that it is a measurement operator associated with a specific outcome or error, right? And it is not necessarily unitary. It is not necessarily diagonalizing the matrix. So those are the wrong answers. So there are like 4 or 5 of you in each question who answered it incorrectly. So please, while you may get a certificate at the end, it may not be very useful if you do not follow up, the questions or ask questions and understand. So please, if you're not understanding, take time to ask questions, or go back and check your understanding from the slides. Okay, so let's get back to our lecture, and I'm going to share the screen. Okay, so we're going to talk about quantum key distribution, right? So here again, we are going to generalize more in terms of what is happening in terms of classical encryption, and then follow up it with quantum, right? So there are infinitely many ways of encrypting information, right? There are thousands of encryption methods that have been realized, and what is done in very early and very simple methods is you have what we call a simple replacement. That is, you replace, like, let's say you can replace A with 1, B with 2, something like that, and then instead of writing whatever, you could write it as numbers, right? That would be a simple replacement. You could also switch, like instead of A, you make that B, so B becomes C, C becomes D, simple encryption like that, so that when somebody sees it, they may not be able to immediately figure out what it is, but with some work, they can be definitely decrypted, right? So first we want to look at some simple encryption systems like this 1:1 mapping, right? So where each character is mapped to some other character. So this 1:1 mapping is something that can be made as easy as you want or as complicated as you want. So it is not necessary that if I have a given quote or puzzle that I can figure out what this entire mapping is, this 1:1 mapping. Because if it is just a short word, right, that doesn't contain all the letters, then I cannot really say anything about it. But if I have a longer, some sentence, then I cannot probably figure that out. So if you have longer sentences, then you can easily figure it out. You also need to know what language that is, whether it is English or something else being written in English, right? So some examples like that, right? For example, if you look at something like this, right? So this is one ciphertext, right? So you see something like this. So it must have some meaning, right? But I cannot decipher what that meaning is unless I have some key to decipher this. Meaning, I need to know what X corresponds to, what Q corresponds to, right? Or what S, whatever that is. The longer the sentence you have, for example, here you have a repeated one, XQLO, XQLO. So that means like there is something that is being repeated, right? the same word. So you can sort of use to figure out as a puzzle. But in real encryption, what we are going to do is I'm going to encrypt, and I also have a key for the encryption, which I will share with the receiver. So the sender encrypts it with some key. The 1:1 mapping is the key, and then this is available openly, and then you can see, unless you have the secret key that we exchange, then you won't be able to figure out what this is. Can anyone figure out what these mean? Are you with me? I could have made a simpler one, but I didn't want to make a simpler one. So are you able to understand me? What we're trying to do here? Yeah. Okay. So let's see, if I give you the map, then you should be able to map the things linearly and see what that is, right? So this is the map. A becomes Q, right? B becomes X, whatever map I have randomly generated, one letter corresponds to another letter. So this is the key. So if I have this secret key, then I can use this secret key to figure out, what those ciphers are, right? Like for example, the cipher text one is Bade Bade Deshon Mein, whatever dialogue, right? Or Mogambo Kushua, right? So you can, that's just I put in just to, throw some interaction in there, right? So you can encrypt it that way, right? But the main thing is this key, right? Unless I give you this key, you won't be able to figure out, what is the cipher text. Sometimes you can, if you know the language that it is written in, it need not be in English, like in this case. That was one of the points I wanted to make. So you may not be able to, easily backtrack what is happening, right? So this is, the basic idea that we're going to express a little bit more mathematically as a one-time pad, often called OTP, right? Which is a classical encryption method that is provably secure. Meaning that provably secure is we can prove how long it takes to crack the key, right? So each bit, whatever information we have, for example, here in this Mogambo Kushua, each letter is a bit I could consider, right? And I'm going to encrypt it with some key. So this M is going to be encrypted with some key. So when I go to the key, M is encrypted as S. So I would put S. O is encrypted as whatever, E, or some, no, O is encrypted as N. So it's going to be N, right? So that I think is very straightforward, that you may even have played as kids or in school. So you can, unless you have the key, you cannot decipher, what that is, right? The decryption is the same process that you do it backwards, right? What that corresponds to, right? If I really generate a truly random key and I use it only once, that is, I don't keep the same key every time. I every time generate a random key and I share the key between the sender and the receiver. And so the receiver has the key, so they can use this random key. Like this is, I randomly map these, right? From A, I randomly mapped it to each other, just making sure that one letter is mapped to one letter, right? So, and the reverse mapping is not the same, right? D doesn't correspond to Q, D corresponds to L, right? Something like that. So if you have the key, then you can decipher it and get these things, right? So if you have like a possible plain text that you have, the 2 to the power n bits, right? Then the plain key you have is like, let's say 0110, the key is this, and you combine it with the cipher, you get this decryption, right? So you would require that the key must at least be as long as the message itself, right? To encrypt and decrypt, right? And so we rely on these kind of crypto systems a lot. For example, when you swipe your credit card, right, there is some information that is being encrypted, right? That is passed on to the bank, and the bank passes on the information to the whoever you're buying it from, and they deduct the money, right? So there are different schemes like this. Like RSA is the most widely used, I think, which has to do with factoring large integers, right? And so these are what we call as computationally hard problems. Computationally hard problem means that the problem is hard to solve, but easy to check. That is, if I ask you to factor some huge number, it may be hard to factor that number, but you can back calculate, and if I give you the factors, you can back calculate and uh, check the answer. So it is easy to check the answer, whether the answer is valid, but it is hard to actually obtain the answer, right? But once you have the answer, it is easy to check that is the answer, right? So therefore, the security of these systems is not absolute, but it only depends upon the limitations of current computing schemes. Because if you want to break this RSA encryption, if you have a powerful computer, then you can break it. It is just that the current computing that we have would require astronomically huge timescales to figure out what these decryptions are. But if I come up with some algorithm that could figure it out, right, it's not mathematically impossible, but it's just limited by the computing power, right? If you have like a powerful enough computer, it could in principle break them. So the problem comes down to this, in a very simple thing, comes down to this key distribution problem. That is, if I have n-bit messages, my whatever one-time pad, one-time encryption that I'm going to use, it requires an n-bit secret key, right? And so how can a sender share it with a receiver secretly and securely, right? If somebody intercepts the key, then the security is broken. They can access it. So when your bank is trying to transmit the data, if somebody can come in and take the data and break that, right? Then that it is hacked. That's what we would say, right? Then the hacker would have all the data that they need. So classical solutions would be like you can have trusted channels, right? So that's what we use. We use trusted channels, secure channels to communicate. Or we have public key cryptography that relies on computational hardness. That is, the key is so long that for you to decrypt it, it would take so long, like millions of years. So then you just assume that it cannot be broken. But that's a limitation of the computing power rather than anything else, right? So again, to mention easy versus hard, right? If you have two large numbers, it's easy to compute the product of two large numbers. But the reverse problem, given n, it is hard to find p and q which factorize it, right? There is no known fast algorithm, right? The immense difficulty of factorization is what actually makes this current encryption, classical encryption schemes very robust. Like I said, that it would take longer than the age of universe to factor simple n completely, right? So that's what is computational complexity theory. So for example, if you have, let's say, some n, which I can write as 2 to the power n, right? So that it has, I can write n would be equal to log to n, right? So digits, right? So that then I can complete that multiplication in a polynomial time. That is the time to multiply the number of steps I would need grows polynomially. That is, as I increase n, it grows polynomially. For example, if I have n is equal to 1, right, the time required to multiply n is equal to 1, n is equal to 5, and n is equal to 10 kind of numbers with those digits would be like, this would be 2, this would be 32, this would be 32 times 32, right? So you can see how it is increasing as you increase that. The reverse of factorization, of multiplication, is factorization. So multiplication again is not okay. Multiplication and factorization. Multiplication is easy to do. Factorization is hard. So factorization goes super polynomially, that is exponentially. That's why we say that the current encryption schemes that are used by the banks or whatever medical data, all that you have, those encryption schemes rely on this, that it takes super polynomial time. That if I have, like, let's say, exponential time, if I have like 1,000 a digit, if n is equal to 1,000, you can imagine how it's going to increase exponentially. So that's why we say that it takes like polynomial versus exponential growth. That if you just double the number of digits, like your credit card is 16 digits, right? So it's going to take, it is effectively uncomputable to break it in practice, right? Unless you try random trial and error and you succeed in hacking. So the limitation of classical key exchange is it is impossible for two parties to classically generate a private key over public channel. That is, if I try to create a private key over public channel, that is not really possible. That you have to meet in person, or you need a trusted intermediate, like a trusted channel to distribute the key. Like, for example, when you pay something on Paytm or something, you see Razor Pay or something that comes up. That is the trusted channel that is taking your information and giving it to the vendor, right? You're trusting, like I'm trusting Amazon, or I'm trusting somebody, some channel to do that for me, to distribute this, right? So that's the one of the limitation, right? So there are security vulnerabilities. So that's why what we want to do is we want to use quantum key distribution, because quantum key distribution is expected to be more robust, and it's also expected to be sort of, you should know if somebody has hacked it. We will see what is the pros and cons of this, and what are the challenges and weaknesses with quantum key distribution. But I hope you are able to follow what we are talking about in general about classical key exchange and why it is hard to break the current encryption systems. Any questions? Okay. No questions. Okay. Then let's see how we generate this. So what we are going to do is we are just using this one-time pad sequence. And what we need to stress on here is that the security here arises from fundamental quantum principle, meaning that you cannot clone the state. We have seen we have seen the no cloning theorem. Right? Does anyone recall why we cannot? What property of quantum mechanics prohibits you from cloning the state? Anyone? What particular feature of quantum mechanics prohibits you from cloning? Very good. Subhanshu says linearity. Does everyone follow? Do you agree that it is linearity? Recall we built, like, if I have a state phi, right? And I can maybe club it with some system psi, which is a n+1 particle system. And I operate this, then I would get a copy phi, and let's say phi1, and some psi prime, and the psi prime becomes an n particle state, and then you get an extra copy here. So we saw that we could do that even for something like phi2, right? Phi1 and phi2. But then if I did phi s, which would be 1 over square root 2 phi1 plus phi2, right? If I try to copy that, right, as phi s coupled with psi, then this won't be equal to doing 1 over square root 2 phi1 with the device plus u times 1 over square root 2 phi2 with the device, right? So these two won't be equal. So therefore, we said that you cannot clone unless phi1 and phi2 are orthogonal, right? That was the one caveat that we used. So we can copy classical information that have orthogonal states, but here the states are not orthogonal. So in general, then you cannot have any cloning, right? So it is because of this no cloning theorem, then we say that you cannot really exactly copy the state. And another thing that we are going to use there is that in quantum, when I make a measurement, right? Again, this is from the Copenhagen interpretation, that I collapse the state, which may not be true. That's one of the weaknesses of how this is described, but we'll get to that later. But when I make a measurement, definitely whatever I'm using, whatever device I'm using to measure the system is going to decohere the system or change the system in some way. So let us say Alice is sending a key to Bob, and the eavesdropper Eve is in between using some sort of a device to read this. And then the device is going to ultimately be coupled and is going to decohere the key or dephase the key. It is going to act like a noisy quantum channel. So we can consider Eve as a quantum channel, the eavesdropper, the hacker as a quantum channel. If it is a classical channel, then you do not know that your key was affected. But in case of quantum, that quantum channel is going to, we saw that the quantum channel can get rid of the off-diagonal elements. In classical probability mixtures, you have only diagonal elements, right? So for example, if I say classical probability, right, now half times I get heads and half times I get tails. So the probability matrix for this would be half, half, 0, 0, right? You cannot get, the off-diagonal elements. So because you have no off-diagonal elements in classical probability mixtures, there is no concept of dephasing or decoherence, right? But in case of in case of quantum channels, we have seen that in general, if I have a system like 1 over square root 2, because we add probability amplitudes and not probabilities themselves, then we can write this in general as P0, P1, C star, where I have off-diagonal elements. So now let's say there is some Eve, Alice is sending this key with some density matrix rho to Bob, right? And let's say there is some Eve, right, that is sort of trying to hack into this rho, right? Then measurements of Eve can be considered as a dephasing channel because any measurement is going to dephase, change the quantum state, right? So if it dephases, then basically these coherence terms are going to vanish. So what Bob receives is actually a different key. So then, Eve cannot make a copy of it, right? It is going to change the system. So you know that your system has been hacked because you would expect off-diagonal element and you don't get any off-diagonal elements, then you know that somehow your state has decohered either due to noise or due to somebody actually hacking it. So in this case, we are actually talking about the quantum channel as a physical channel. Are you able to follow? Any questions? Are you able to see the difference between classical probability mixtures versus quantum? Okay, that's good. So there are several, quantum key distribution protocols that have been proposed. And BB84 is something that was proposed by Bennett and Brassard. The paper was published in 84, so it's called BB84. And B92 is Bennett published in 92. Eckert is using entangled pair of qubits. What we will do first is this BB84, right? So we can use how many ever qubit signals we want to basically do the two pairs of non-orthogonal state, right? So we will first focus on this BB84 protocol and try to see what that scenario is. So what we are trying to do is we have Alice and Bob who communicate using a public classical channel and send quantum bits using a quantum channel. Eve is the eavesdropper. Eavesdropper can be accessing the public classical channel as well as the quantum channel. And the goal of Eve is to get whatever is the key without being detected, that is without being known. Or, even if Bob comes to know that, Eve may not have gotten the key, but if Bob comes to know that there was interference, then you can discard and send again, right? So the result of this quantum key distribution is that it is impossible for a hacker to break into the channel and get the key by any means without introducing detectable disturbances that that the key has been hacked, right? There was one meme sometime back where somebody says that, oh, all the data has been hacked, and then they open the computer and say where the data is not stolen, it is here only in the file, right? So when you make a copy, classically you cannot tell the difference. You have the original there, right? So, but in case of quantum computing, we are saying that if somebody makes a copy of a file, we would know that they have made copy of a file because in doing so, they have changed the they have introduced detectable disturbances, right? So first we are going to start with our 4-qubit states and their mutually unbiased basis. So that is, we are going to pick two different bases. One basis is what we call as horizontal, vertical, or top, upper, down, or 0, 1, right? So we're going to pick 0 and 1, right? This is one basis, right? And the other basis is plus or minus basis, which is plus or minus meaning they are the superpositions of 0 and 1, right? So we're picking two bases. So this is basis 1 and this is basis 2, right? So, or basis 0 and basis 1, whichever way you want to call it, I have. So the first one is just the Pauli Z basis. That is, 0 is, you can consider as, so the 0 state would be something like 1, 0, and 1 state would be something like 0, 1, right? And so that's what we call as Pauli Z basis. And the other one is called the Pauli X basis, because whatever you have along Stern-Gall arc in up, that would resolve into both up and down along the x-axis. So we have these two different bases, right, that are offset from each other. So this is the basic point for BB84 protocol, that you have two different bases. And Alice and Bob can pick whatever basis they want, right? So we have Alice on one side and Bob on other side. And Alice and Bob can pick whatever basis they want. They can pick B0 or B1. And these two bases are mutually unbiased, and measuring any state from one basis in other basis yields outcome that are equally likely. What that means is, for example, if I measure 0 state in plus basis, right, then I would get plus. If I do on 0, I would get half, right? If I do plus on 1, that also will give me half, right? Are you able to see that, right? So the probabilities will remain the same. So they are equally likely, right? So then, so this would be 1 over square root 2. The probability would be square of that, so that would give me half, right? So what we are going to do is we're going to look at how Alice is going to generate her key. So they're not actually sharing the message itself. The public communication channel has a message. They're the encrypted one. They're sharing the key. That's why we are calling it as the key distribution problem, right? So let's say Alice generates two uniformly binary strings where each of these x1, x2 till xm, each of these is 0 or 1. Similarly, we have y1, y2 till ym, each of this is 0 or 1, right? So one of these represents the actual value that is going to be the key, and other one, y, represents what basis she is using. And she need not use the same basis for each bit, right? So first bit she can encode in basis 0, that is 0 or 1 basis. Second bit she could encode in plus minus basis. So she can use different bases for each bit, right? And then based on that, she is going to use m qubits, that is the key has m, length m. So for each bit, she is going to use 1 qubit to encode the key. And then these qubits are going to be transmitted to Bob over a quantum channel, right? And she's going to pick all these things randomly because it's a key, right? Some random key. And the bases or all these are going to be picked randomly and sent to Bob. Were you able to follow that? Any questions? Any questions on step 1 or so far, whatever we have discussed? Okay. Okay, I hope everybody is able to follow the things. So here we are assuming that this channel for now is noiseless, that there is no noise in this other than, like, meaning when I say noiseless, I'm not considering the eavesdropper or the hacker as noise. That I consider it as intentional, whatever they're trying to steal the data, right? That's not just environmental decoherence or something. Yeah. So we're considering otherwise, if there is no eavesdropper, this quantum channel is noiseless. So let's say an example. Let's say Alice wants to send 6 bits. So her key X is encoded as 1, 0, 1, 1, 0, 0, whatever random key she generated. And so she is going to generate, for the 6 bits that she wants to send, she is going to generate another 6-bit string, which is again randomly generated. And the second 6-bit string that I have, that is Y, is indicating the bases that she will choose. Remember, we have 2 different types, B0, which is 0 and 1, right? And B1, which would be plus or minus bases, right? 2 different bases. So then, you can make a table, right? So the first bit is 1, and the corresponding, the first bit is, let's make this table. So this is I is telling me which bit it is. So the first bit is the first bit that I want to send is 1, and I want to send it in the basis given by the first letter in Y. So that would be the 0th basis. So what is 1 in 0th basis? 0th basis is 0 and 1. So the state that qubit I'm going to send is 1. Right? And the second bit is 0 in X. So I'm going to put 0, right? And the corresponding basis is 1. And so 0 in 1 is the plus basis, right? So then I'm going to send plus as my second qubit, right? So same thing, like you can repeat that for all the other ones. And so then Alice is going to prepare these 6 qubits that correspond to the 6 classical bits. And this yi is the random set of bases that she has chosen for each basis, right? So she sends these 6 qubits to Bob over the quantum channel, which is noiseless. Any questions on how we got this? Were you able to follow how we assigned, how we prepared the qubits? Are you with me? Are you able to follow? Okay. Okay. Are there any questions? Okay. So then if there are no questions, let's go to second step. So let's say Bob receives and Bob is measuring, right? We assume no eavesdropping and a perfectly noiseless channel. Now Bob will generate some sort of a basis for himself, which is again random, right? So Bob is going to generate. Bob only knows that he's going to get a 6-bit signal, right? So he is going to generate a uniformly random bit, a random string that is going to give him whatever his bases are. This does not match with whatever Alice sent. So like Alice picked whatever Y, like 0, 1, 0, 1, 1, 0. Bob has no clue of what this is yet, right? Bob is generating his own 6-digit code, right? So Bob is going to generate that, right? So let's say Bob generates his own one like this, 1, 1, 0, right? Bob generates Y prime, which is 1, 1, 0, 0, 1, 0, right? And then he receives whatever message that is sent by Alice, and then he is going to measure whatever 6 bits he gets with whatever Alice sent. Okay, and then he is going to write down the result that he is going to get. Right. So let's see. The 6 bits that we sent. Let me go back up. So what Bob is going to receive is if it is a perfectly noiseless channel, Bob is going to receive these qubits, 1 plus 1 minus plus and 0. So these are what Alice sent, right? Those were encoded in whatever bases that Alice picked, right? And this is Y prime, which is a random string of bits that Bob picked, irrespective of what Alice picked. So now as Bob gets these bits from Alice, then he's going to measure the first, what Bob is going to measure is the first qubit. Bob is getting is 1, and Bob's first basis is 1, right? That means this is plus or minus basis, right? One basis is plus or minus basis, right? So what Bob is going to find is Bob is going to measure this, and Bob is going to find that when he measures it in plus or minus basis, how would you express state 1 in plus or minus basis? That would be basically 1 over square root 2, right? Plus minus minus, right? So he's going to find that is the state, right? So he's going to get that is the result, right? He's going to get half for plus and half for minus, right? That's the probability he's going to get, right? Then the second bit is plus, right? And the second basis is also plus. Second basis is also plus. So then he is going to get 1, right? Because plus state, he's measuring in plus state. So plus plus is going to give him 1, right? Similarly, the third bit, right? It is 1, right? And it is being measured in 0th basis, which is 0, 1 basis. So again, he's going to get 1, right? So on and so forth. So for whatever Alice measured, right? He also measured in his own basis, right? And he got his own result. Are you able to follow me? Any questions? Okay. Okay. Now then, Alice and Bob, what we're going to do what we're going to do is we're going to check whether Alice and Bob are going to compare their bases, right? And then check which one matches, right? They're going to just compare their bases, right? Yi and yi prime. They are not comparing the qubits. They're not sharing the qubits over public channel. They're sharing only their basis channels over the public channel. So then they know that, okay, here I use the same basis or not, right? So in this, for the second bit, both of them use the same basis. So wherever they use the same basis, pick only those digits. So then you will pick only those qubits. So then Bob and Alice will both see that, oh, okay, second basis is the same. So they should have the same result. That is, both of them should have 1, right? Now, if somebody interfered with this state, right? If somebody interfered with this plus state, the second thing, right? Then Bob would have gotten a different result. Because if somebody interfered with that plus state, let us say they decohere it and the off diagonal terms are gone, right? And so when Bob gets it, he's not going to get the answer to be 1. He's seeing like some off diagonal elements are gone. Then basically then they know after they have shared the basis keys, right? They should get the same answer for the second qubit because Alice prepared it in the same basis as the measured basis of Bob. So ideally, if there was no eavesdropping, they should get the same result. But if there was eavesdropping, then that is you have dephased or decohered the state, and so Bob will get a different result, right? So then if Bob got a different result, then basically then you know that somebody interfered with this thing, right? Are you able to look at follow what I'm saying? So they compare the bases, they discard the bases where they did not have any matching. So they would discard bases like 1, 4, and keep bases only like 2, only 2 where the bases are matching, or 3, or 5, or 6. So their result should exactly match. So now if they randomly pick 1 bit from this, right, after discarding whatever bases did not match, they reduce the 6 qubit to 4 qubits. Now, if they randomly share, like if Alice randomly says, my second qubit is 1, and Bob sees that his second qubit is not 1, then that means somebody interfered with the key. Somebody tried to hack him, right? And so that's how you can know that that there was some sort of a hacking that went on, right? So you can do some sort of a classical post-processing if there are quantum channels which are not perfect. And this is why we were trying to model the dephasing or decoherence. Because if I have, let's say, a fiber optic cable over which I am sending some light pulses, and the polarization of these light pulses is what I can encode as a qubit, right? So I can prepare light in horizontal or vertical polarization states, or I can prepare that in left or right circularly polarized states. 2 different bases like plus minus or 0, 1 basis, right? And then I have a fiber optic cable, which is a standard fiber optic cable, and then I can use that channel. I send a lot of these bits in the lab and see how the decoherence happens in that channel without an eavesdropper. I test it. I model that decoherence, right? And so I know the decoherence of that, just the fiber optic cable itself, the physical medium itself. So I do understand that, if I send state one, because my fiber optic cable is not ideal and it has some sort of decoherence, then Bob may not get one, Bob may get some difference. The off-diagonal elements may be different for Bob, right? But if there is eavesdropping, then I know that those off diagonals have changed beyond whatever I have modeled for my fiber optic cable. Are you able to see what I'm saying? That I can model the fiber optic cable itself with a quantum channel by performing. This is a standard fiber optic cable with this core, this cladding, and so I can make measurements on that, and just the basic cable itself, I could say, induces a certain amount of noise. If Bob finds differences that are beyond this noise level, then you have a different interference, right? And the way we how do we measure? We introduced a characteristic scalar to measure this, right? That is the fidelity metric, right? I hope you are able to recall fidelity metric. The fidelity metric basically tells me how faithfully I have reproduced the state. So I can introduce a fidelity metric for my fiber optic cable itself. So let's say, an ideal fiber optic cable would be 100%. That is, fidelity would be 1, right? But a real fiber optic cable maybe only be 90% fidelity. But if Bob is getting the state with anything less than 90%, like Bob gets it with 70% fidelity, then obviously that means that it is not just due to fiber optic cable, but it's due to some eavesdropping, right? Are you able to see that? Are there any questions? Are you with me? Are you able to follow that? Any questions? No questions? Okay, that's cool. I guess maybe you guys have studied this before. Eve intercepts the qubits, and the problem for her is that the basis may be different and she doesn't have these things. We'll come back to these eavesdropping attacks later. But what we want to do is, let's go back to the code. So what we would like to do is, I have this code for the protocol. So I'm going to paste this in the chat box, and we will try to generate on a real quantum computer and try to see how we can do the BB84 protocol. So please, you can get the code. I think that didn't paste properly, so you can use this one. You should be able to see the code in chat, and it's also on the screen here. And so please open and run it on your own, and you will need to change the API key and CRN. So here what we are going to do is, first we are going to just map our problem to a quantum circuit, right? So first I'm going to install install Qiskit, right? And then I'm just setting up a random generator to generate step one, right? I'm setting up a random generator that would give me this X or Y, right? That you can see here. So I'm generating these Xi or Yi, right? So, and then I'm going to generate for 20 bits, right? 20 bits. And so I need, because I need to pass on 20 bits. If I have to pass on 6 bits, I need 6 qubits. If I need to pass 20 bits, I need 20 qubits, right? So I'm going to take 20 qubits. I'm going to build a quantum circuit. And so this is just initializing 20 qubits all into 0 state, right? And Alice's bits, A bits or Alice's bits, right, would be whatever. You're just going to round the random numbers, right? So you just get between 0 and 1. excuse me, between 0 and 1, 20 such digits. So that's what is going to give us Alice's bits, and Alice's base would also be the same thing. So and so if Alice's bit, you choose based on that, you pick this. And so if Alice's bit is A bits is equal to 0, and if A base is N is 1, then use the Hadamard gate, because Hadamard gate is what will put it in plus or minus state. Right? Do you see that what we are trying to do here? If bit is 0 and base is 1, you put a Hadamard gate. If bit is 1, base is based on how whatever you are trying to do, right? And then Bob is also going to prepare similar bases, right? Are you guys able to hear me? Since the internet connection is unstable, so I hope. Okay. So it got stuck between. So I hope for a few seconds, I hope you are able to follow what I was trying to say, that basically it is generating okay, let's see here. So basically it is generating whatever we have, multiple qubits, and I am generating 20 qubits, and based on if n is 0, that is the bit is 0 and base is 1, or bit is 1 and base is 0, different combinations. If basically if the base is 1, we apply a Hadamard gate. If base is 0, then we just send it as such, as 0 and 1. Then you apply just a NOT gate to make it 1, right? Otherwise you send it as 0, right? And so then Bob is also going to get his own basis and make measurements. So let's see, I'm going to generate whatever, and I'm going to print Alice's bits. Alice's bits are 0, 0, 1, 1, and her bases are the same thing, right? And Bob's bases are given here, right? So you can see where they match. So for example, Alice's third base and third base in Alice and third base in Bob match for me, because we are generating randomly. When you see it for on your code, they may be different. Are you able to follow me? Are you with me? So I see that the third base for me, third base for Alice and third base for Bob, they're matching, right? So whatever Bob measures on the third bit, that result also should match, right? If there is no eavesdropping, right? Then, like that, we can compare what bases are matching, and we can see that for those, Alice and Bob's result should match. So if I draw the circuit, right? So this is what I have. That is 0th qubit. Alice's base is 1. So we used a Hadamard gate, right? And then Alice's second base is also 1. So we use a Hadamard gate. Alice's third one is 0. So we used X base for that. So 0th base is X base, H base is base 1, right? So you can see like different bases that we used so that we get whatever result that we need to get. And Bob is measuring whatever he needs to measure, right? So here, please change your instance on this and your API token in this code, so you can run it on your own this thing. And so I'm going to just start the service and pick a backend. I'm going to pick IBM Brisbane, and then now we're going to do also a noise model, right? So we are going to simulate and generate noise based on currently selected backend. That is whatever IBM Brisbane, it has some noise. We're going to generate that noise from that. So that noise model is generated from the decoherent Krauss projectors that we discussed. So that noise model is a quantum channel, like how we did with, so somebody basically performed several times and use that to generate a density matrix or the Krauss representation for that, and that's how you're generating from there. And then we are going to transpile our qubits so we can pass them on to Bob, right? So and then we are going to run them through the sampler, right? And so what sampler is doing is now Bob is taking time to measure these things, and then remember that you have to reverse the order of qubits, because the qubits in Qiskit are sent right. So we write from right to left, left to right, and the other way is apt for qubit. So for us, qubit 0 would be the first qubit on the left, but for on Qiskit, qubit 0 is the first bit on the rightmost side. So we reverse the order. So these are the bits, right, where we are getting out of 20 bits. I got 3, 6, 9, 12, 15. So 20 bits. I got 20 bits that I measured. Out of these 20 bits, all the 20 bits will not match because Alice and Bob may have chosen different bases, right? So now we want to separate only the good bits from it where the bases match. So here they publicly share the bases, right, to identify the good bits. So once they have publicly shared the bases, the bases match in these things. So now you see that Alice and Bob have the same key. So you have a fidelity of 1 and no loss at all. This is on a real quantum computer we ran, and we were able to get good fidelity because we were filtering out, we're doing the measurements immediately. So it's sort of a fake channel. We are doing it within few nanoseconds of whatever measurement, right? So so that's not really going to do anything. So now let us see, we include Eve, an eavesdropper, right? And I'm going to take like 127 qubits. Okay, let's change this. I was running just for fun. So let's say 20 qubits. So again, let's run this. So now what we have is same thing exactly, but in between, we'll have, so this we are getting fidelity 1. There is no problem with uh, anything there. So let's put Eve inside. So here we have Eve. So what Eve is doing is Eve is going to pick her own base, right? So Eve is going to generate a random string of bits, and that is going to give her own base. And based on whatever the thing, if it is Hadamard base, if it is base 1, she is going to measure in Hadamard. Otherwise, she is going to measure in X basis, Z basis, whatever basis she wants, right? But before we pass on the qubits to Bob, we are making a measurement with whatever basis is chosen by Eve, right? So that is what we are doing, right? So and then after that, we are sending it to Bob, right? So then let's see what happens, right? So once Eve has measured and then Bob reads, if it is going to change or not, right? So let's see. I'm going to run that, and then we will see that if Eve has interfered, then when she measures some state, then that state would change because of the measurement that Eve has made, right? So we'll wait for some time to see what is happening. And then you can run it with 127 qubits also. It doesn't take much time. It takes some computational time, but it does work. And it is nice to see. Okay, it's going to take some time. But in all these, one thing that you need to notice is I am using only one shot, right? I'm only using one shot that I highlighted here. So it may yield, the real quantum computer has noise, so it will yield. So we lucked out because we are using 6 qubits. So if you try to use 127 qubits, you will see that the fidelity is very poor. Like here for 6 qubits, the fidelity is good. But if I run the same thing with like 127 qubits, for shot 1, the fidelity may not be good, because if you make only one shot measurement, you may get different result every time you generate something, right? So So now after Eve have put in, right, see, we get 0.6 fidelity. So there is 0.4 loss. So then they know that because the fidelity has decreased, then I could say that, somebody has eavesdropped. Were you able to follow that? Are you with me? Any questions? So let us change this to, instead of 20, let us change this to 127. And let us see. So this is no Eve in this. This is just 127 qubits without Eve. So Alice so before we were getting fidelity one, let us see if we will get fidelity one with 127 qubits. What do you think? Should we get fidelity one if there is no Eve? See, we got less than one little bit, right? So if you run it again, you might get a different fidelity. So that would really depend upon the run, right? See, even with 127 qubits, I got fidelity one. And here, let us see 127, right? And let's see. What kind of fidelity we would get. See, there's 0.6 and 0.4. So you're losing clearly a lot of error is creeping in. So then you know that that somebody has tried to eavesdrop, right? Were you able to follow that? Any questions? I guess there are no questions. Was everybody able to understand what we were doing? Are we still connected? Okay. Yes. Okay, great. So I hope it is somewhat hard to judge whether the students are understanding or not in a virtual class. That because I cannot see you. And so thank you for responding. So I hope you will try this out yourself and try to do with multiple shots and see what you will get. In each shot, how many shots, like, again, we are measuring immediately, right? So in reality, you have to delay, right? Because from Alice to Bob, it will take some time. So try to put in a delay in this code, right? So this second part of the code is Eve is listening in. This part of the code where we got fidelity as 1, here try to add delay in there somewhere, right? So Bob extracts bits. So before Bob extracts bits, add some delay, right? You can add a delay. So figure out how to add delay. That was there in one of the codes that I sent before. Figure out how to add delay and see if you add a delay of 100 nanoseconds to 1 microsecond to 10 microseconds, will you still get fidelity 1 without any eavesdropper being in there? And how would that change if you have a real delay between Alice and Bob? Then how would that affect the fidelity with and without eavesdropper? So that is an exercise for you to try out. So once you go home, you can try that out and check that out for yourselves. So I will stop here. That basically concludes quantum key distribution and why, how we can see eavesdropper effects as dephasing or loss of fidelity. And I encourage you to play around with this code, make a copy and play around with this code. Like I said, try to do multiple shots, try to do multiple delays. And again, this is like a project that you can take up. And like if you're a master student or a BTech student, maybe this could be a project that you could write up and submit as, whatever, I don't know, for your class or for something, right? It's interesting to do such things, and maybe you can even submit as a paper to some journal if you try to do something novel enough in this. But you have the tools and resources to do that, and so please play around with these codes and see what you can do. Before you come back tomorrow, if you can do these delayed measurements and tell us whether the delayed measurements are inducing any loss of fidelity, that would be nice. So I'll hang around if you have any questions. If you don't have any questions, that would be all for today. Thank you. Okay. So how Eve is getting to know about number of qubits she doesn't have to get to know about the number of qubits. She is just measuring as they come by, right? It is going to be one by one measurement anyway. So she's just generating some random long number of digits, right? So she doesn't need to know how many qubits. Many strong hands-on Python library. Uh, um, Rajneesh, there is a quantum machine learning on IBM website. So we will not probably be able to cover that, but you may want to look up. If you go to the IBM quantum learning platform, you must have already created the ID. So on that, you can check out. There is if you go to modules, there are courses and there are modules. If you go to modules, there is a module on quantum machine learning where they train the CNN using a quantum neuron rather than the classical neuron. So you can look up that to do for projects on quantum machine learning, for example. I hope that helps. Any other questions? Okay, in that case, I'll see you guys tomorrow. Tomorrow is the last lecture, so please try to bring as many questions as you have and pertinent to the material. And we will discuss if you have any questions pertinent to the material tomorrow. If not, tomorrow we will try to do some of the quantum algorithms, basic quantum algorithms, and then we will also try to do some practical applications that these qubits have been used for. Okay, all right. I'll stop there and see you tomorrow. Thank you.